Okay, so in 6.6, one of the big things that we're going to be doing is playing around with these rational exponents, meaning exponents that are fractions. So instead of having an exponent of 2 or 3, you could have an exponent of 1/3, 2/3, 1/2, things like that. So we're going to just take a look at something like that. So like b to the 1/2. We're going to see what exactly that means. Try to figure out what b to the 1/2 would be equal to. So the first thing that they will show in the book, if you look at this explanation, is they'll take it and say like, okay, so let's take this expression and let's square it. Because we know how the powers work. If I take this and I square it, my powers tell me that I can multiply these two together. So if I multiply 1/2 times 2, I just get 1. And we know that b to the first is just equal to b. So whatever this is, when I square it, I end up with b. Well, one thing we also know from previous sections is that squaring and square rooting are opposites of each other, so we also know that this is true. We know if we have the square root of something and we square it, then we just end up with b. So if I square this thing and get b, and I square this thing and get b, they must be the same. So a conclusion that we can draw here is that b to the 1/2 must be the same as the square root of b. And so what I'm going to write right here kind of extends that to any power, 1 over n, so 1/3, 1/4, things like that. So b to the 1/n looks like this. b to the 1 over n is just the nth root of b. So for example, we could also write, like x to the 1/3, and that is the cube root of x. Or we could write a number in there and simplify that up. So that's the way that that works, and we'll be able to simplify using the same exact properties that we used with square roots and cube roots and everything like that. Okay, so one thing that we can do is writing back and forth between radical form and exponential form. So what I just wrote here, the b 1 over n equals the nth root of b. The one on the left, we call that exponential form. The one on the right we call radical form. So this is exponential, this is radical. So one of the examples that you guys will be doing is just going back and forth between the two of them. So this is currently in exponential form. To write it in radical form, we know that 1 over 7, 7 would then become the index right here. So here, like 7 is n, so we write it like this. So this is the same as the 7th root of a. We're not responsible for evaluating. In this exercise, we're just simplifying them down. And then here's square root of w. Remember, anytime you don't see an index, you technically have an index of 2. You'll never see that written. You'll never see like second root. It's always just square root. But because the index is 2 and it's written in this form, you can say n is 2 and write this as 1/2. So this is w to the 1/2. So the first thing in your homework you'll be responsible for doing is just switching back and forth between those two and just getting comfortable with radical form versus exponential form. Okay, negative exponents. We've got the same thing with negative rational exponents. So remember, if you have anything, x, let's say, and it's being raised to a negative power, we would flip it down to the denominator. Okay, so we'll be doing that with these as well. So for part A, for example, 49 raised to the negative 1/2 power means we write 1 over 49, and then we can write that exponent as being positive. So we do this little trick anytime you see a negative exponent. So we flip it like that, and then we go back to this up here. So 1 over n here is 1/2, which means we write it as the second root, which is the square root. So this is 1 over the square root of 49. So this relationship right here tells me that these two things in the denominator are equivalent. And then we should recognize the square root of 49 is 1/7. So what a negative 1/2 power means is you square root it and flip it. Because the negative means you flip it, the 1/2 means you square root it. So if I take 49 and square root it, I get 7. If I flip that, I get 1/7. So that would be my final answer right here. Okay, 32 to the 2/5 is kind of similar, little weird. So if we recognize the 32 right here as some sort of larger power, what we want to do, something that can help us out, is write it as a power. So we can write 32 as 2 to the 5th. Okay, so that's what I'm going to do. I'm going to write 32 as 2 to the 5th, and then keep that power of 2/5. Okay, so this little trick will actually make things a lot easier on us because one of our properties says that we multiply these exponents together. And if I multiply 5 times 2/5, these 5s will actually cancel. And this would be the same as 2 to the 2nd. And 2 squared, of course, gives us 4. So that means 32 raised to the 2/5 power gives us 4. Okay, so This one worked out really nicely because I could write it as 2 to the 5th and then the 5's canceled, but that won't always be the case. So we could also see situations where we have some sort of base and then we have m over n. So not just 1 over n, but we could have m over n. And so the pattern, the way that this works, is we can kind of split up those two pieces. All right, so we think of this as splitting the m over n into m times 1 over n. And believe me, this is actually headed somewhere. It's important that we rewrite it like that. So m times 1 over n, we can put that in a different order. So we are going to write 1 over n times m. And then remember, one of our properties says we can picture it like this, like big set of parentheses here with this on the outside. So if we run backwards this way, if I multiply these two powers together, I get 1 over n times m, which is the same as this. And then if I multiply m times 1 over n, I get m over n. So these two things are the same, but writing it like this will actually make it way easier to simplify. So I could have done that right up here as well. So let me show you kind of an alternate way following this pattern right here. I could have written this as 32, and then I could split the 2/5 into 1/5 times 2, and then just grouped apart this piece first. So 32 to the 1/5, if I follow this pattern right here, 1/5 means 5th root. So the 5th root of 32 squared. 5th root of 32 means what multiplies by itself 5 times to give me 32, and that would be 2. And 2 squared, just like I wrote in the other version, of course gives me 4. So a couple different ways to look at that. So I'm going to write this version down too, so I can think of this as the nth root of b raised to the m power. So anytime you see this, you know it's the same as this. So that would be a good thing to just memorize as quickly as you can. All right, in this last example here, we've got this nice formula. It's a mass formula. You see right here, we've got a rational exponent of -8/5. It says it estimates the maximum total mass that a weightlifter with b kilograms, that'll go there, can lift using clean and jerk. According to the formula, what is the maximum that a weightlifter weighing 168 kilograms can lift? Okay, so we're going to take this, plug it in here, and we will actually just use our calculator to evaluate. So I'm going to show you in this one how the calculator works with this. So m equals, we've got 512 minus 146,230, and then for b, I'm going to sub in 168, and I'm keeping that exponent of -8/5. So like I said, I'm going to show you just how to sub this right into the calculator. So we've got just a blank calculator screen here. I'm going to type in the 512 minus 146,230. And then just like it's written, in parentheses, I'm going to write the 168. So make sure it is in parentheses. And then our important key here is this little caret key. So look at the 4 and then 2 buttons over. That little caret key, if you type that in, you can put any exponent you want. So we're going to type -8 divided by 5 as our exponent. And hit enter. And so we get 471.8 approximately. So 471.8. And that would be in kilograms. Okay, so in the second section of 6.6, we're going to be simplifying up these expressions with rational exponents, and we're going to use the properties we learned. This should be in 5.1. So let me flip you back real quick to what I'm talking about. So it's the very first section of 5.1. I'm sorry, the very first section of chapter 5, and we had all of these properties. So just to run through them really quick, if you've got a base and 2 separate exponents, you add them. Quotient, you subtract the properties. Anything negative, remember, gets flipped, or vice versa. If it's in the denominator, it gets flipped up. If you've got a power raised to a power, you multiply them. Anything with multiplication or division on the inside, you can distribute that property to both pieces. And then anything raised to the 0 power is 1. So we're going to be using all those same properties. If you lose track of any of them, just feel free to flip to this section 5.1. For now, we're going to simplify up some of these sections. So 2 really important things to remember. Rule number 1, any negative exponents get flipped. So if they're already in the numerator, they get flipped down. If they're in the denominator, they get flipped up. But either way, they get flipped. And then second rule, is anytime that you have something in the denominator, any exponents in the denominator must be positive integers. Okay, so any in the denominator must be positive integers. So they must be positive just because of this rule right here. Anything negative would get flipped. And they must be integers because any fractions represent some sort of root, square root, cube root, whatever, and we're not allowed to have roots in the denominator. It's got to be positive and it's got to be an integer. So let's practice some of these properties here. So example 4, part A. Remember the rules that I just flipped and showed you. If we have the same base and then two separate powers, one of our properties tells us that we add those powers together. So we've got y. Our new power will be 1/7 plus 4/7. Since they have the same denominator already, we can just add them together and we end up with 5/7. 5/7 doesn't reduce. That's really about all that you could do for your final answer, is you would just leave it like that. X to the negative 2/3, if we're following some of these rules, negative exponents get flipped. So we are going to write that as 1 over x to the 2/3, but if you're following the second rule, any exponents in the denominator have to be positive integers. So this is now positive, but it's not an integer. So what we have to do is basically like rationalizing the denominator. We have to make sure that we have a positive integer in the denominator. So if we want this to go from 2/3 up to 1, we would multiply in an x to the 1/3. So now our denominator will be taken care of because we'll add those exponents together and we'll end up with just a power of 1. But remember, you cannot just multiply the denominator without also multiplying the numerator. So we're multiplying in what we call just a fancy 1 here. Same thing, numerator and denominator. So numerator, 1 times x to the 1/3 is just x to the 1/3. And then here, remember, just like this property, I add 2/3 plus 1/3, and I get 3/3, which is just 1. So that is now just an x. So now I'm following both of the rules that I have here. So these are my final answers for both of these parts. All right, so let's this last one. One other rule to keep in mind, remember to use the least index possible. What that means is, like, if something was written as a 4th root but you could actually simplify it, you should do that. So we'll see an example right here. So 6th root of 16 and then over the cubed root of 2. So we've got a lot of simplifying that we can do here. So first of all, 16 is a power of 2, so we're going to rewrite it that way. So we've got 2 to the 4th. That's what 16 is written as. So we've got the 6th root of 2 to the 4th and then over the cube root of 2. So just to help simplify, I'm going to write those exponents as fractions. So remember, the 6th root of 2 to the 4th means you can write 2 to the 4/6 power. So any index just becomes part of the fraction when you're doing these. And then this 2 to the 1/3 is the cube root power. All right, so let's keep simplifying. This 2 to the 4/6 will reduce down to, this is a 2/3. 4/6 just reduces down to 2/3. And then we've got 2 to the 1/3. So now finally we can use one of our properties that tells us if we've got the same base, we can subtract. So subtracting, lucky for us, these have the same denominator, so I can just very easily simplify that to 2 to the 1/3. So that's the same thing as the cube root of 2. You can write it as the cube root of 2 if you want it, or you can just leave it as 2 to the 1/3, whichever you want to do. All right, this one here, same sort of thing. We are going to write 4 as 2 squared and then see how that simplifies. Okay, and then remember that 6th power means that we're taking the whole thing and raising it to the 1/6. 6th root is the same as the 1 over 6 power. So now I've got another property that tells me I can distribute that 1/6. So 2, I can multiply 2 times 1/6 and I get 2/6 as my power. And then times x to the, and then 4 times 1/6 would be 4/6. So I can keep on simplifying. So I've got 2 to the 1/3 because that power reduces down. Same thing with x to the 2/3. Okay, so now see how they both have that 3 in the denominator? That means they're both cube rooted. So you could leave it like this, same thing like we did here, but I'm going to show you just a different way that we can simplify. So 2 to the 1/3 means I've got a 2 under a cube root. X to the 2/3 means we've got an x squared under a cube root. So this is the most simplified that you can write something like that. So just kind of reducing down this power into this. Okay, last one here. This is like a rationalizing the denominator thing. So I've got y to the 1/2 minus 1. That's not a positive integer, so I need to change it. And what I'm going to do is something that I did in the previous section, and I can multiply top and bottom by the conjugate. So the conjugate of y to the 1/2 minus 1 is y to the 1/2 plus 1. So top and bottom, same thing. Okay, so I'm going to FOIL both pieces. So y to the 1/2 times y to the 1/2. Remember, you add those exponents. 1/2 plus 1/2 would be 1. So that's just y to the first, or y. Outside, y to the 1/2 times 1. Inside, another y to the 1/2 times 1. And then 1 times 1 for the last. And then the denominator, very similar. First, 1/2 plus 1/2, I add those exponents and I get 1. Y to the 1/2 times positive 1. Inside is y to the 1/2 times negative 1. And last is negative 1 times positive 1. Okay, so you'll see these cancel, which happens every time we use the conjugate. It gets us to simplify our denominator. And then in the numerator, we have y. There are 2 of these y to the 1/2s, and then a plus 1. And my denominator is just a nice y minus 1. So these two things are equivalent. I just had to change the way it was written because I'm not allowed to have that 1/2 in the denominator. So this is a quick just summary of all of the simplifications that you should be making. You should have no negative exponents, no exponents that are not positive integers. We've been talking about both of these. Not a complex fraction, meaning a fraction of fractions. And then the index is the least number possible. So we did that with something like part B.